No. Okay. So today we're going to talk about the 3D moment at an axis. This topic and Friday's topic are both on the upcoming exam. Our learning objectives is to define the attributes of a concurrent force system. And actually, we already did that when we did the dot product for force vectors. It just means if it's a concurrent force system that they intersect, right? So we have this intersection that they intersect there. And then we just need to be able to calculate the moment at an axis for a system with one or more forces. Actually, moment at an axis is exactly the same thing that we did with the dot product. We're just using moment vectors now instead of using force vectors. So to give us an idea of like what kind of how this relates to reality, here's a problem here where they ask us to find the moment of each force acting on the handle of the wrench about the a-axis. And actually the a-axis right here is the axis about which, if we can find how much moment we're exerting about that axis, that's going to be the moment that unscrews that end cap there. So we have this person that's applying these two forces here about the pipe wrench, and we want to figure out, well, how much are those two forces actually exerting on a moment that would unscrew that end cap or that pipe cap right there. And so instead of just finding the moment about a point, like say we found the moment about this point right here, well, that might be a moment vector that's like pointing off like that. That might be the moment vector about point C, but we want to know, well, how much of that is actually exerted down onto or projected down onto that axis. And so we're going to do the dot product again, just like we did before. Here's that's a canvas example. Here's another canvas example. This one is really similar to the homework question here, where we're asked to find, given a force that's applied out here, how much moment are we getting along this axis over here? How much of that is exerting a moment along that? And then this one, we're asked to find the moment about the axis from A to B. So how much moment do we get along that axis down there? That's for our homework problem. And then here's the homework problem that's really similar to that canvas problem. The canvas problem is under the supplementary example problems posted up on Canvas. In this one, we've got this force that's exerted out here, and they want to figure out how much moment are we exerted about this segment of the pipe here. If you look in right here, it says to hit suggestion, use a scalar analysis. I disagree. You have to do all the same, you need all the same information to do a vector, and then you don't have to figure out what your moment arms are and what direction they're causing a rotation about. So I would do a vector approach on that one. So let's write down our procedure. And so number one here, and I'll rewrite this with you. So number one is to calculate the moment at any point on the axis of interest. And we just finished last time talking about how we calculate a moment at any point. For example, MA is equal to R from A to B cross the force at B. And this MA just has to be any point on the axis of interest. So if they tell us, you know, the axis of interest is A to C, or something like that. So it's any point on that. So we've already done that part. And then we've also already done step number 2 over here. Number 2 is to find the projection of the vector, and it really should be the moment vector. We'll do the moment vector onto the axis of interest. And so how did we do that before? We just did that with a dot product. So we could find the moment about the axis is going to be MA dotted with the unit vector along the axis. So it's exactly the same thing that we did with forces, right? It's just a vector dotted with the unit vector, and it gives us a scalar, doesn't it? It's going to give us a scalar. Now, if I wanted to convert that into a vector, wouldn't I just take my scalar magnitude, m-axis, and multiply it times the unit vector again? So if I want to convert that into a vector, same process that we did with forces. I see some people in today's front row with their cameras on. Awesome. Thank you all. Prash and Bryce and John. And it looks like John has a young pupil.
I have a visitor, yes.
Yeah, we have a visitor. John has a visitor today. We make sure she does the quiz too, okay? Or he does the quiz. I think it looks like. Okay, so let's we're gonna jump into. Did everybody get that down? Okay, go ahead, Kaylee. Okay, I think that should get both. Okay, so we're gonna do the same example as last time, but we're just gonna have a slight modification. And now for the moment add an axis. But so we all know what our physical system looks like. We'll use the same thing. And so we are given in this problem here, remember we had the x-axis going off to the right. We've got the y-axis going straight up, and then the z-axis coming out of the page. We had our pipe assembly that went along the x-axis. It makes a right turn and goes straight up in the y direction, and then makes another 90-degree turn, and it goes straight back into the z direction. So just like I have over here, right along the x, straight up parallel to the y, and then straight back into the z direction. And we'll take our same force. We have our FD up here, and that is equal to a 10I plus an 8J, and then minus a 4K hat, and that's in units of pounds. So we got all that. And then we're gonna add a segment of pipe. The plumber called over the weekend, and they were like, oh, you know what? We need to add a section of pipe in here. And so we're gonna add a section of pipe that goes from about there down to about here, and we're going to call this point where it connects in, we're going to call that point E, and we're going to call this point down here point F. And so let's see, then we had still from last time point A, and that had coordinates of 0, 0, 0. Point B was right here, that had coordinates of 2, 0, 0. Point C had coordinates of 2, 3, 0. And then point D up here had coordinates of 2, 3, minus 4. So A, B, C, and D coordinates are all the same. F has coordinates of 2, minus 1, and 5. So you can kind of visualize, right? That's going in the positive X. It's going in the positive or negative Y and positive Z. And then point E has coordinates of 1, 0, 0. So it's halfway. E is halfway between A and B there. So really, if I on my picture over here, I don't have my new pipe assembly, but it kind of comes off like that. I did it in black on the picture, right? So my new segment of pipe is coming off like that. It's not shown in the picture there. And then we are asked to find, for this one, the moment vector along E to F from that force up there at D. So for our solution, we go back to the procedure that we wrote down. We know that we can find the moment about e to f is going to be, right? It's the moment about any point on that, right? So it's going to be the moment vector dotted with a unit vector. We know that's our starting equation, right? It's a moment vector dotted with a unit vector. Last time we had found the moment about point A. Can we use that moment about point A? Prash, what do you think? Can we found the moment about point A last time. Can we use that in this dot product?
I think so. Maybe. I'm not quite sure.
So remember the moment about point A was here, wasn't it?
Mm-hmm.
It was right there, but we're looking for this axis over here. And and it has to be concurrent, right? In order for us to do the dot product. So we can't use MA, but what 2 points could we use for this one?
E and F?
Yeah, we could use E or F. Which one looks like it's going to be easier to take the moment about?
E, probably.
Moment about E. Yeah, so let's take the moment about E because just the coordinates. I'm just looking at the coordinates of E. It's 1, 0, 0. I could take F. I could take the moment about F. That would work too. Because remember, we can go to any point. We can use any point on the axis of interest. And then the unit vector here is going to be along that axis, which is the unit vector from E to F. And we could use F to E as well. But we're going to use, I'll go ahead and use E to F. It doesn't matter which one we use. Okay, so now we figured out, okay, that's going to give us the moment about E to F, the scalar. Now, we need to find ME, right? So ME is equal to the position vector crossed with the force vector. Now they told us to use the force vector at D. And so now where does R need to start and end if we're taking the moment about E? John, what do you think?
I don't know.
Well, remember if we're taking the moment about E, where does our position vector have to start?
At E.
At E, yeah, it's just that straightforward. At E, and then so it has to start at E, and then it can end. Remember, at any point on the line of action. The only point that we know on the line of action of the force is D. So R from E to D crossed with F to D. Now we can actually combine these two steps, and we can combine these into what's called the triple scalar product. Because don't we know that ME is R cross F, and actually ME is that part in there. So our M from E to F is equal to R ED crossed with FD. And then that whole thing would be dotted with a unit vector from E to F. Now I'll show you the way we do that, the way we combine those. We'll look at that once we get all of the vectors that we need here. So let's write out our vectors. R from E to D is going to be equal to final minus initial, right? So in the x direction, it's going to be 2 minus 1. So 2 minus 1 in the I. It's going to be a minus 1 minus 0. So minus, or we'll go plus a minus 1 minus 0 in the J, and then plus a 5 minus 0, 5 minus 0 in the K direction. And so our R from E to D is going to be a 1I minus a 1J plus a 5K hat. I feel like I did something wrong there.
Are we supposed to use point D and not point F?
Oh, yeah. That's what I did wrong. I used the wrong. I was doing E to F, wasn't I?
I think so.
Can we, I think the easiest thing then, why don't we change this? I was thinking, I was saying one thing and doing another. Why don't, this is not E to D. Isn't that E to F, which we do need as well? But instead of working on the position vector, or E to D, we're working on the unit vector from E to F there. So then we can find our unit vector from E to F is the position vector from E to F, which is what we just found, divided by the magnitude from E to F. And so this is going to be a 1 minus 1, 5 divided by the square root of 1 squared plus a 1 squared plus a 5 squared. And this is going to give us a 0.192i minus 0.192j and a plus 0.962 k hat. Okay, and then does that answer? Yeah, point D, not F. I saw some stuff in the chat there. Does that make sense what I did there? I just found the position vector from E to F, which we needed anyways, and then we found the unit vector. Okay, and now we can find the position. Now we can go back to actually what I was trying to do originally, was to find the position vector from E to D, which would be the coordinates of D minus the coordinates of E. And that's going to give us, let me see if I can scroll. Let me zoom out just a little bit here where we can see point E coordinates. Oh, I can't. So it's going to be, right, 2 minus 1, 3 minus 0, minus 4, minus 0. And so that position vector that we're going to end up finding there is going to be a 2i plus a 2j minus a 4k. Okay, any questions on that?
Can you look back at the graph? I just got a different position vector. Maybe
Yes,
my points are wrong.
Let's go look at that. Okay, so we have, it would be, I'll do it in blue. It would be 2 minus 1, right? Final minus initial. So it'd be, oh yeah, x, y. Yeah. Man, I'm killing these vectors today, aren't I? Okay, so it would be a 2 minus 1 in the I. And then a 3 minus 0. Two minus 1, a 3 minus 0. Okay, yeah, wow. And a 3 minus 0 in the J, and then a minus 4 minus 0. Minus 4 minus 0 in the K. So let's see, this is not correct. This is not correct. I'm 1 out of 3 on that one. So why don't we scratch that and let's rewrite the position vector from E to D. And so that's going to be a 1i plus a 3j minus a 4k. Is that, am I right now? Yeah? Okay, good. Because I have used, this is not the first time I have used this example, and that is the first time that we have caught that mistake. Interestingly enough. So nice work to those of you that are paying attention, even with all these, even through a computer screen. Okay, so now we have everything for our triple scalar product, which remember is this R from E to D crossed with the force at D, and then dotted with the unit vector from E to F. Now the way that we can do that is, remember when we did the cross product, we had an IJK across the top row. Well, instead of putting IJK across the top row for our cross product, we just put the components of the unit vector. So 0.192, a 0.192, and a 0.962. And this works because we're just going to multiply. We end up, by doing this and still following the same operations as a cross product, we end up multiplying the I component of the moment vector with the I component of the unit vector. And so then our next row is going to be a 1, a 3, and a -4. That's our position vector. And then the next row is our force vector, which we were given as a 10, an 8, and a -4. So we have our unit vector from E to F is this one right here. We have the position vector from E to D is there. And then we have our force vector at D is there. And so when we solve this, we are going to get a scalar, but we just follow exactly the same operation. So instead of putting an I here, like we would have done with the cross products, I'm going to put the 0.192, and then that'll be multiplied by this 3 times a -4 minus an 8 times a -4. And because we found this error, I'm going to need some help doing these calculations here. So 3 times a -4 minus an 8 times a -4. Then remember, we always have a negative in front of the J. That extra negative, so then it becomes a negative 0.192. So we have two negatives out there, and then a 1 times a -4 minus a 10 times a -4. And then our last one is a K. We add that, we don't have the extra negative on the K, 0.962 times a 1 times 8 minus a 10 times 3. And so we're going to end up then with a, let's see, 0.192 times a -12 plus a 32. We're going to end up with a plus 0.192 times a -4 plus 40. And then our last one here is going to be a plus 0.962 times an 8 minus 30. So what do we get? Let's see. We basically have a 20 times 0.192 for that first term. Does anybody have the... If people want to start throwing stuff in the chat or turning on your mics there, while I try to do these as well. But I'm probably going to end up making an error. Okay, so the first one is minus 10. Well, how can the first one be negative? Wouldn't the first one be positive? Because it'd be really a 20 times 0.192. I get 3.84. Okay, I. Yep, 3.84 I. And then we basically have a 36 times 0.192. Positive, or no, that would be, yeah, that one would be positive too. Positive 6.91. And then we have a minus 20 times 0.962. A minus 19.24. Now these are not, oh sorry, and I saw the I in there. Now these are not, I need to correct something again. This is Correction Wednesday apparently. These are not I, J's, and K's, right? This is a scalar. All this stuff over here is a scalar. So this is just going to give us a magnitude, and maybe that's what somebody had originally posted, because if we take the 3.84 plus a 6.91 minus 19.24, we get a negative 8.49. And that's foot-pounds. Because remember, we get a scalar out of this. You get 5.84. 3.84 plus 6.91 minus 19.24. I get negative 8.49.
I think, at least for me, I got a different value for the last one, the 0.962 times 8 minus 30. I got negative 21.164.
Oh, thank you. Okay, so 22 times 0.962, 21.164?
Yeah.
21.164. And then this makes the overall thing negative what?
I got negative 10.412, but you might want to check that.
Okay. Anybody else get that?
Yep, I got that too.
Awesome. Yay, we did it. Which is the answer I have written down in my notes. So I'm not sure. I don't know what's going on. I'll look at that after class. Okay, but let's look at now our answer. So what this is saying is, just conceptually here, if we go back to our picture right here about this segment of the pipe, there is negative 10.4 foot-pounds that's trying to break that thing off, or just trying to unscrew it. Now, which direction is it going though? Is it trying to unscrew it this way, or is it trying to unscrew it that way? And how can we tell? We can tell based off of the sign here. That negative, just like we did with forces, when we use the dot product and we got a negative magnitude of a force, it means that the moment vector points opposite the unit vector that we use, which was the unit vector from E to F. So it's actually saying that the moment vector is pointing from F to E. And so then we could use our right hand and we could say, oh, well, our moment vector is pointing up this way. We point our thumb in that same direction and we know it's trying to spin the pipe that way. It's trying to spin with our thumb pointing from F to E. So just like we saw with the dot product and forces. Okay, now we were asked, we go back to our original problem statement, we were asked to find the moment vector from E to F. To do that, we take our negative 10.41, we keep that sign, and we multiply it times the unit vector again. It will fix everything for us when we keep that negative sign in there. So for example, it's going to be a minus 10.4 times our unit vector is 0.192i, a minus 0.192j, and a positive 0.962 k hat. And so look at what happens when we keep that negative 10.4, we end up with a negative 2.0i. So, and which way we talked about, the moment vector should be going from F to E. And wouldn't that have a negative x component? To get from F to E would have a negative, right? We would have a positive in the j, positive 2.0 in the j. because it has that f to e has a positive. To go from f to e, you'd be going in the positive y, and then we would have a positive 10 k hat. Take that negative, or sorry, no, that should be a negative. We end up with a negative k hat there because, right, that f to e is going in the negative direction. And then also if we wanted to find like cosine alpha, cosine beta, wouldn't we take a minus 2 divided by, what would we use down here? Would we use a negative 10.4 or positive? Positive or negative? We're going to use a positive. Okay, so this one is always positive, even if we find a negative. Even if we find a negative with the dot product, that one is always positive. These ones up here, though, are based on are based on whatever signs we have in the vector. So this is from the vector. So we will use a negative 2 in that case. For cosine of beta, it would be a 2 over 10.4. And then for cosine of gamma, it would be a minus 10 over 10.4.